Hello everyone, my name is Sahil Khose and today I'm presenting you our 15th video on the channel. The paper we'll be discussing today is in the domain of natural language processing and zero-shot learning. The paper we are looking at today is a paper from Google Research which was released on arXiv on 3rd September, so around a week, 10 days ago, and the paper deals with zero-shot learning in natural language models, and it is titled "Fine-tuned language models are zero-shot learners." The model that we'll be talking about in this paper, they have named it FLAN, FLAN, which is Fine-tuned Language Net, and let's get ahead and get into the paper. So the main motivation of the paper is exploiting the ability of zero-shot learning ability of these large, massive language models that have been coming out in the natural language processing community ever since BERT came out. So in 2016-17. So what like one of the most prominent examples of like the amount of just the amazing results that we get in a zero-shot paradigm was seen by us when GPT-3 by OpenAI was published, and when that model came out, it's one of the largest models, one of the largest language models that we have. It has around 175 billion parameters, and the zero-shot capabilities or the few-shot learning capabilities of this model was fascinating. So what do you mean by that? So GPT-3 is basically trained on the entire corpus of the internet. So whatever scripts we could find, scrape the entire internet, and we basically trained a 175 billion parameter model on the entire data. Now the data wasn't particularly curated in let's say just choosing filtering the language English. So if you have a script, if you have a textbook, then it could have different language sentences in it. So what we observed after we analyzed the models, or we tried to benchmark it on various data sets, we found out that GPT-3 was able to perform very good on even translation tasks, and we hadn't particularly provided any other language data set in the self-supervised fashion that is all these language models are learning, and we hadn't provided any specific learning task for the model or a specific language data set either. But we saw that if we just prompted convert the following sentence into French, and we gave it "my name is Sahil," and the GPT-3 promptly, through its next word prediction capability, it could translate the given input sentence into French, and that is amazing. So the model wasn't particularly trained on this or even on French corpus, but there were bits and pieces of French or other languages in the corpus that was majorly around 90% English or more, and still the model was able to learn a task which it hasn't been trained on or particularly given the data for. So this is an example of a zero-shot learning capability. Or another fascinating thing that we observed after GPT-3 came out was its ability to add two numbers. So we could so the way the language models such as BERT and REST, including GPT-3, have been trained is very simple. It's you provide a large text corpus to these models, and you have just one loss function for the training, or like one objective. There could be multiple losses, but there's just one objective of the model, that is to predict the next word in the sentence. So it's taking an input, textual input. Let's say it takes half the sentence, then it has to just output a softmax over the entire dictionary that it has of the probabilities of the next word, and the maximum probability, or through some beam search method, we find out or we complete the sentence by predicting the next word continuously. So it can be used for generation tasks or even inference tasks. So that was the only objective all of these large language models have been trained on. So this would be a self-supervised fashion and self-supervised learning. So what we found out was, if we gave GPT-3 a prompt of, let's say, what is 1 plus 2, it had never seen any, we hadn't particularly given it the data set for any of such tasks, but it still used to perform these calculations and give the answer. And not just single digit additions, but like even complex multiplications or divisions. I think it was weak on multiplication and division because it was complex, but we got very fascinating results with addition and subtraction of even 2-digit numbers in GPT-3. And the reason that the authors thought was there was some data in the corpus which had these mathematical tables in it, and people interpreted this capability of GPT-3 in a way that GPT-3 has learned, has seen so much data that it has gained some intelligence, and it is able to, so it's not just retrieving the sample that it had seen earlier and producing the result, because the answer it was giving was spot on. So even if there was no instance of, let's say, 21 plus 31 in the entire corpus, it would still give the right answer. So in a way, it wasn't fetching these data samples that it had seen before, but it was understanding how these additions were performed and the subtractions were performed, even like two-digit numbers, and it was able to give correct answers. And people, the authors went ahead and searched for the corpus if these examples existed, and they didn't in a lot of cases. And this means one thing, which is GPT-3 was not just learning, or was not just fetching the older data that it had seen, but it was actually learning the intuition of how to do these additions and subtractions, or some complex mathematical equations. And that is fascinating. So this is like this is one prompt, or just a show of intelligence being showcased by these large language models. And that's, so all of these examples that we talked about are like the zero-shot tasks that GPT-3 had performed, and this really impressed a lot of people. And so this topic is what we'll be talking about in this paper. So what the authors of this paper did was, they suggest in this paper, they suggest a method which is called instruction tuning, which is used to train their model. It's a pre-trained, they take a pre-trained language model, they use this method called instruction tuning to train this model on particular tasks, and it benchmarks its performance on unseen tasks, so as to get a zero-shot benchmark. And they compare these zero-shot benchmarks with the zero-shot benchmarks of GPT-3 and with few-shot benchmarks of GPT-3, and they get fascinating results. So the language model that they have used is 137 billion parameter language model, and they train it on use this instruction tuning on 60 NLP tasks. And after they evaluate this model, which they call FLAN, with the GPT-3 model, which is 175 billion parameter model, it outperforms GPT-3 on 19 of 25 tasks in a zero-shot benchmarks, and on few-shot benchmarks, it outperforms GPT-3 on 10 of the tasks. So just training this model in a zero-shot fashion, you have the zero-shot benchmarks for this model on 19 of 25 tasks. Compared to GPT-3, it outperforms in the zero-shot benchmark that GPT-3 has, and on 10 of the tasks, this zero shot benchmark that this model sets, it outperforms even the few shot benchmark that GPT-3 has set. So in a few shot paradigm, what we have, instead of the model never seeing a data instance of the data, you give it one or two or multiple few instances of the task that you want to perform, and then it quickly learns over it, generalizes, and it gives us the benchmark. So that's really like that's the essence of the paper. That in the entire paper they show how they go ahead and what's the instruction tuning method and how the tasks are divided in like seen and unseen tasks and how did the benchmark. But the entire paper is about how and in which tasks this FLAN model outperformed GPT-3 on zero shot and few shot learning benchmarks. All right, and we at the end of the paper we also have ablation study where we see how the number of tasks and the model size affects the performance of this model called FLAN. Fine tuning on many tasks. Sorry. Instruction tuning, one example is there. We have the input. This is a common sense reasoning. We have an input and we have two options. Like the input is, here is a goal, get a cool sleep on summer days. Question is, how would you accomplish this goal? Options are keep stack of cases in fridge, and second option is keep stack of pillowcases in oven. So obviously A answer should be the one that the model predicts, and like the target is the A answer. All right, so or like we have a task which is translation, and it's like translate the sentence to Spanish, English input, and target is in Spanish, and you have a lot of tasks. Now to change this into the instruction tuning paradigm that they have used, so to change this, so they haven't given a one-to-one example. I was assuming they would have. So this is not a one-to-one example, but in the like this is the tasks on the left are the type of data sets that FLAN or any language model sees, and on the right we see the instruction tuning framework. So we have a premise, we have a hypothesis, and the prompt is, or the instruction is, does the premise entail the hypothesis? And you have three options, and the FLAN's response is, it is not possible to tell. So yeah, we'll look at the graph. In graph we see that FLAN zero shot is outperforming both zero shot and few shot benchmark of GPT-3. Again, reading comprehension, the same thing. Open domain question answering, it performs better than GPT-3's zero shot, but few shot it's a bit like 2% less performance. All right, now we'll get into the introduction. We see Finetuned LAnguage Net is called FLAN. They use the base language model that they use is as we saw before, it's 137 million parameters, and they use this instruction tuning to improve the performance, and the final model, resulting model, is called FLAN. And yeah, we'll just skip the introduction. We'll go to the pre-trained. Even this diagram explains us how fine tuning will happen. So normally have a language model, pre-trained language model. You fine tune a task, you have the objective that the language model should perform well on this task, so you train it in a supervised fashion, and then you have the inference. That's how you get a benchmark. So you have BERT benchmarks, fine-tuned benchmarks, ahead will go, and another model fine-tuned benchmarks. So that this would be fine-tuning. Like in a supervised fashion, you train the language model on the task that you want to perform. Then prompting, so you have pre-trained language model and improve performance via few shot prompting or prompt engineering. We'll see at the end, in the last evaluation study, we'll see how prompting or prompt engineering all performs better on FLAN instead of the base language model. And the instruction tuning that this paper introduces is like on pre-trained language model, instruction tune on many tasks which are not a part of the cluster of the task that we want to evaluate on, so that the task that we are evaluating on becomes a zero-shot benchmark. So we'll see what this instruction tuning is, and yeah. What we have in instruction tuning or in the FLAN, this paper, is we have 62 text data sets, as you can see in the diagram, and there are two types of data sets. One is two types of data set. One is language understanding type of data set, and another is language generation tasks. So I think the color is like blue and teal. So the natural language understanding tasks from here are in blue, and the three on the right, so the four struct to text, translation, and summarization, these three clusters are generation tasks. So these are the task clusters. So these are, all of these are like 62 different text datasets which are publicly available on TensorFlow datasets, and there are 12 different clusters according to the type of dataset it is. So if it's natural language inference, the different clusters are as follows. So natural language inference, common sense, sentiment, paraphrase, open domain question answering, reading comprehension with common sense, co-reference, miscellaneous, summarization, struct to text, and translation. So all of these clusters have different datasets in it, and these datasets are called tasks. So there are 62 different tasks or 62 different datasets that we have clustered into 12 different task clusters. Now the way we work in the paper, you train the model, is you select, let's say 10 or like 9 or 10 different clusters, and you have 2 or 3 different clusters which are separated. You have 9 plus you have like 9 plus 3 splits. Okay, now you'll train your model using the method that they have suggested on 9 of these clusters, and then you will evaluate its performance on the 3 clusters that are separated in the beginning. So that would be the zero-shot benchmark that we have. And we also train our model on these 9 clusters in a way that first we start with the cluster or like the data sets which have a large amount of data, and we train on them first and slowly move towards the data sets or the clusters which have lesser data set. So because the reason for this is the tasks that have a larger data, the language model will be able to learn a lot in the beginning and slowly fine tune with the less amount of data that we have, so that it doesn't forget the newer task or the data sets with few data just because it has seen the other tasks or the clusters more frequently. So we start with the most frequent tasks and go to less frequent tasks, or which is dependent upon the amount of data points that the data sets have. And after every task or after every cluster, we evaluate it on the 3 clusters that are separated. So that would be the zero-shot benchmark, and in this way we measure the performances, and we'll look at the results after this. So these are the tasks and templates. These are the tasks. Now we look at the templates. So how you create this template? So template is changing this changing a particular task into a instruction template for the training process of this FLAN model. So the way so we'll look at that. We'll look at few of the instruction templates. So template 1 is like we'll look at the normal data set. 1 second. Yeah, sorry. So we'll look at the multiple instruction templates in like for changing the given data sets into natural language inference task. So we have the data set on the left, which is premise, hypothesis, and target. So we have a premise which is a text, then we have the hypothesis, and the target is entailment or not entailment. So does the hypothesis is true or not over the premise? So options are yes or no. Now to change this type of data into our templates would be as follows. So we have the premise, then we have hypothesis. We have to figure out what the hypothesis is given the options, and our template 2 can be infer the following, and we have the hypothesis, premise, options. Then we have the premise given, then you mention premise as premise. You have an instruction given which is read the following and determine if the hypothesis can be inferred from the premise. And you have the premise, then you have the hypothesis, and then you have the options. So options in this particular type of task, what we have is we have options. And now when we ask the language model to predict over the entire distribution of the dictionary, then we just select what is more probable, if yes is more probable or no is more probable. But the this is not effective, because the model could be maximizing probability over the different words in the dictionary which mean yes, or which infer that yes, this premise is the answer for this premise hypothesis task is yes. So it could be distributing all the probability over the words that are aligned towards the yes option. So the yes word itself wouldn't be getting a lot of probability distribution, and similarly with no. So unfairly, no could get a higher probability just because it doesn't have a lot of examples for it to maximize the probability on. So that's an issue. So to overcome this issue, what the authors have done is whenever they have options to select like yes and no, at the end of the input sequence that they have a token, options token, and then which is followed by the words which are the options. So list of words which are the options, and then the model has a understanding that okay, out of these words I have to select which word is the more probable, and by that they solve this issue. And by doing this they get a really good result. So by this they get a really good result. So we'll go ahead and see the evaluation splits now. So evaluation split, they just say that you have a few tasks or clusters which are unseen and few clusters which are seen, and you train on the clusters which are seen and you evaluate on the clusters which are unseen. Now classification with options. Okay, that's what I just explained, that we have options suffix as you can see here, and followed by a list of outputs. Then the training details. Model architecture and pre-training. So the model type that they have is dense left to right decoder only transformer model, and this model was trained on so they tell us what the model is trained on, and approximately 10% of the pre-training data was non-English. They mention the paper where this model was used from, and they say that this pre-trained model is called as base LM everywhere. This is 137 billion parameter model, base model. Now for instructions for instruction tune procedure. So how we have, they again reiterate that it's an instruction tuned. So FLAN would be the instruction tuned version of base LM, and for preventing it from overfitting, because some data sets have millions of samples, others like commitment bank has only 250 samples. They used example proportional mixing scheme from 2020 paper of Raffel et al, and the mixing rate maximum what they use is 3000, and they use add factor optimizer and all of the details. So alright, so that's all with the setup. So the setup is as follows. Tasks, we have different tasks, different clusters. Then we have templates to translate this data set into these templates. So for every task you have 10 different templates which does the same thing, and you have 3 more templates which reverses the task. So let's say if you have a sentiment analysis task, and you will have templates which say, okay, what is the sentiment of the following instruction, or what is the sentiment of the this review on Amazon, and like followed by the instruction, followed by the review, and it will give us a couple of words. Now there will be like 10 different templates of how to ask the model, or what instruction to give the model to answer this question. But there will be 3 more templates which reverses the tasks. So what means is let's say the answer of the sentiment analysis question is there is a review and the sentiment is negative, and it's a movie review. So the 3 templates will be like a flipped manner. So can you generate, we'll ask the template will ask the model, can you generate a negative review of the movie, whatever, and then it changes from an inference task to a generation task. And using these, so they have like a random method to select which template to be used while training on every data instance, and that's how they cover all the clusters that are used for training purpose. Then you have evaluation splits, seen and unseen. Then you have classification with options. If you have different options, it could affect that it's not able to give us a good argmax. So we add option suffix and then a list of what it should predict from. Then training details, we saw a base LM model and FLAN model, which is instruction tuned, and what it does for class imbalance. Now we'll look at the results. Results are pretty simple in this, in a way that every single section in this in the results is on what tasks it outperforms GPT-3 or even supervised BERT. So we'll get into it now. So natural language inference, FLAN outperform. It is going to be the same story every single section of this. What tasks it outperformed GPT-3 and what it didn't. And yeah, let's get started. Natural language inference, FLAN outperforms 0 and few shot GPT-3 on 4 data sets by a large margin without any prompt engineering, and with best dev template. So they have different templates. So if they choose the best template, then FLAN outperforms a few shot GPT-3 on all 5 data sets. So like obviously if it's outperforming few shot GPT-3, then it obviously outperforms one shot GPT-3 as well. And FLAN even surpasses BERT on ANLI R3. So the comparison that we had was just 0 shot and few shot of GPT-3, but BERT was specifically supervisedly trained on this task, and it still outperformed the highlighted yellow. It still outperformed, the FLAN still outperformed the supervised BERT model. And next is reading comprehension and open domain question answering. FLAN outperforms GPT-3 by a large margin on BoolQ or OBQA, and FLAN is slightly higher than a few short GPT-3 when using the best dev template on multi-RC. Then we have ERC easy and ERC challenge, where FLAN is substantially higher on both 0 shot and few shot GPT-3, and on natural questions, FLAN outperforms 0 shot GPT-3 but does not outperform few shot GPT-3. And here are the results. Going ahead, common sense reasoning and conference resolution. This isn't a very strong point. This is a strong point of FLAN because there wasn't it matched the performance, but it didn't outperform any. And going ahead, translation, few short translation results were comparable again with GPT-3, and compared with GPT-3, FLAN outperforms 0 shot GPT-3 for all 6 evaluations, though it underperforms few shot GPT-3 in most of the cases. So this is again the results table. Going ahead, all right, so all of these were the results tables. Now we'll look at the ablation studies and that they have done. So there are 3 ablation studies. There are 3 ablation studies that they have done, and we'll go towards we'll look into it. The first ablation study is number of instruction tuning clusters. So what they found out was, as I mentioned before, they were training the instruction clusters one after the other, and they were evaluating the performance on the unseen clusters. So as they were adding newer and newer clusters, what they found out was the performance always on the zero shot clusters always increased. Even after after every single cluster addition, it always increased the performance of the model on zero shot clusters. So that was the result, that even after you're adding a lot of clusters, the model is able to generalize well, and hence it's performing well on the zero shot clusters. And clusters, as I mentioned before, clusters were added in decreasing order of number of tasks per cluster. Second, they figure out that after adding even all the clusters, they found out that this improvement in the accuracy or performance was steady, and they hypothesized that we could still add more clusters if they are available, and this will still increase the performance that we have on zero shot or few shot clusters. And that's the result, or that's the hypothesis that they get from this first ablation study. So you look into the this is the table that describes it. So this is the addition of different clusters. There are 7 clusters, and it's evaluated on 3 held out clusters. So 7 plus, and the green is the average performance. You can see the average performance is always increasing. Common sense is increasing, NLI, open domain queue is also increasing. So with addition of every single cluster, the performance on the held out data clusters is increasing. Second ablation study is scaling laws. So what they do is, in Brown et al. 2020 paper, it shows that zero and few shot capabilities of language models substantially improve for larger models. So they do this FLAN study on 5 different model sizes: 4 to 422 million parameter, 2 billion parameter, 8 billion parameter, 68 billion parameter, and 137 billion parameter, which is their main based language model. So what they do is, again, they add instruction clusters one by one, and they evaluate on the zero shot cluster that they have. And what they find out was, instruction tuning improves by a large margin over the untuned model without instruction tuning. So in every single case, for every model size, all of the 5 model sizes, instruction tuning will improve your performance over the base model every single time. And on the scene clusters, so the clusters it's been instruction tuned on, every single time it will improve the performance on the scene task that we have. But on held out task or the unseen clusters, it's a bit different. The observation is different. So the largest of the 2 models, which is 68 billion and 137 billion parameters, they substantially improve the performance on held out tasks. But it is not the case with the 3 models which are smaller. So it's actually the contrary. So what we have is, the performance on the held out tasks improves when you do instruction tuning on 68 billion and 137 billion parameter models, but it decreases, the performance reduces in 3 models which are smaller in size. So the instruction tuning hurts the performance on held out tasks. And the potential explanation that the authors say is it is the result of small scale models, that learning around 40 tasks during instruction tuning, it fails the entire model capacity, and it's not able to learn more and generalize more. So it causes the model to perform worse on newer tasks. And for the larger scale models, instruction tuning fills up some capacity of the model, but it because the capacity is so large, it also teaches the models the ability to follow instructions, and this generalization allows them to perform well on the newer tasks which are unseen with the remaining capacity. So we'll look at the tables that showcase this. So untuned models, 5 models, how they are performing: 0.4 billion, 2 billion, 8 billion, and 68 billion, 137 billion parameters. What were their average accuracy on the held end tasks, and the held end tasks after instruction tuning, in every single scenario you can see it's improved, and the larger the model, the better it's performing after the instruction tuning. But on held out tasks, after instruction tuning has happened, only the largest two models perform better than the untuned model, but it decreases the performance on the unseen classes. And third and final application study of this paper is instruction tuning facilitates prompt tuning. So they try prompt tuning. So as we have seen that instruction tuning improves the ability of the model to respond to instructions that we have seen in the templates before. So it follows that a FLAN is indeed more amenable to performing natural language processing tasks. So it should also achieve better performance when performing inference using continuous prompts, which is optimized using prompt tuning. So they analyze this by training the model continuously on continuous prompts for each of the superglue tasks, and they see the performance. So you have they train the base LM and the FLAN on using prompt tuning, and they see the result. And what they found out was every single time FLAN performed better after prompt tuning, after being optimized through prompt tuning, than the base language model. And this was especially true when the setting was a low resource setting. So especially for the low resource setting, prompt tuning on FLAN even achieves more than 10% improvement over prompt tuning over the base LM. So that's the end of the aberration studies. Related works, they mentioned some, and discussion, they just conclude what we have seen in the paper. So the paper has explored a simple question in zero shot prompting: does instruction tuning a language model improve? Does instruction tuning a language model improve its ability to perform unseen tasks? Obviously, the answer is yes. Our experiments on FLAN demonstrate that instruction tuning improves performance against an untuned model and surpasses zero-shot GPT-3 and even few-shot GPT-3, along with a couple of instances where it outperforms the supervised BERT model. And through aberration studies, we also learned that performance on unseen tasks improves with the number of task clusters. So as we are increasing the number of task clusters, the performance on unseen tasks, or like the zero shot benchmarks, it increases. But if you are comparing it with the size of models, then only the last two models, which were around 100 billion parameters, only those two perform better on the unseen tasks when we train in this method. And moreover, the final aberration study, we see that it's better, the FLAN responds better to prompt tuning than the base model, especially when the resources are low. So this entire idea of prompt tuning, of changing every single data set and task into a fashion where we give prompts to the language model to solve a particular problem. So just unifying all the data sets that we have in a prompt tuned manner, and then providing this data to the model, it really helps it understand the prompts and how to answer the particular prompts. And this prompting is extremely useful when we go and benchmark these models on the zero shot tasks. So we can just give a prompt and then it will give the answer for the particular prompt. So it's understanding of prompt, generalizing how to extract the answer for different various prompts, and training the entire model on just the prompt tuning, or not the entire model, a pre-trained language model, fine tuning it on this prompting prompt training is it gives us really good results in zero shot and few shot benchmarks, even better than what we saw in GPT-3 and supervised BERT model as well. So that's the end of the paper. That what concludes it. Thank you everyone for joining. This will be our 15th video, and I have, as usual, if you go to the description of this video, you will have all the timestamps for different chapters. You'll have the annotated paper link. You'll have the link of this paper on archive, the repository as well. They have made the repository public, but the code isn't available, but you'll still get it when they update it, because it's just been 10 days that they have created the repo and published it on archive. And along with that, you'll also have links to my website and other socials, and also the annotated paper that you saw in this video. You'll have that as well. Thank you everyone for joining. Thank you everyone for watching. Thanks everyone for the support that I've gotten in the last 15 videos, and have a good night. See you in the next one. Bye.